Hello everyone, welcome to Semiconductor Device Simulation. This is lecture 4, Drift Diffusion Equation. In this lecture, I'm going to introduce you how to solve a drift diffusion equation along with continuity equation. So there are different type of method to solve it. I'm going to introduce you the Slabun variable and how to couple drift diffusion equation with the continuity equation and how to apply boundary condition and how to self-consistently solve it with Poisson equation. I'm also going to introduce you another way to solve drift diffusion, which is the Shafter-Gamma discretization. Finally, as always, I'm going to show you some code. In previous lecture, I have introduced you what is drift diffusion equation and how to derive it. And so now we will have a drift diffusion equation for both N and P. And if we want to solve a continuity equation with drift diffusion under steady state, how should we discretize Jn and Jp? So since here you can see that we're going to plug in some divergence of Jn into our continuity equation. And to discretize that, we need to obtain the Jn at I plus 0.5 point as well as I minus 0.5. And can we directly write our drift diffusion equation at I plus 0.5 as this form, where we have this N at I plus 0.5. And they say that we want to simply approximate this N plus 0.5 using the average between I plus 1 and Ni. And the answer is no, we cannot directly do this. Since this way to approximate our N at I plus 0.5 is a very bad approximation. Since N can vary exponentially between these 2 points, so this approximation is very rough and will make our solution become unstable. One way to solve this issue is the so-called Slabun variable. In this approach, we are going to solve for EFN and EFP instead of N and P. In previous lecture, I have talked about that we can write Jn and Jp using EFN and EFP. And one thing to be noticed that this expression of Jn and Jp does not rely on Boltzmann approximation. Even if using Fermi-Dirac statistic, we can still rewrite it as these two forms. And under Boltzmann approximation, N equals to Nc exponential EFN minus Ec over Kt. Then by plug this N into our Jn equation, we got this form of Jn. And now we were going to define a variable phi n equals to exp of EFN over Kt. And this phi n is the Slabun variable. By defining this phi n, we can further simplify this equation of Jn using phi n. So our Jn will now equals to this equation. So now you can see that for all these things before this gradient of phi n, there are just some variable. We are not going to solve for it. So we are only going to solve for phi n, and which is discretized and can be able to apply to our continuity equation and solve for it. And for Jp, we can also simply define a Slabun variable phi p as exponential minus EFP over Kt. And we'll also be able to rewrite our Jp using this phi p. This method can also be applied to Fermi-Dirac statistics. Under Fermi statistics, N and P will be expressed using Fermi integral. And the problem now is that we cannot separate EFN and EC from this Fermi integral, but we can still using stubborn variable by defining this phi n equals to exponential EFN over KT. So now we need to times this exponential EFN over KT and divide this function to this Jn, so that we will be able to rewrite our Jn into this form. And now we define this Fermi function over exponential function as our gamma n. And then you can see that we end up with some equation very similar to the equation we have in the previous slide. Then here we have this exponential EFN over KT and a gradient of EFN. We can use this stubborn variable to rewrite this equation to this form, and it is very similar to our previous equation, except that now we have this gamma n instead of exponential function of EC. But one thing to be noticed that is, usually when we are going to solve for the drift diffusion and the continuity equation, we are expect to solve for a linear equation instead of a nonlinear one. However, now in this gamma n, we have nonlinear function of EFN. So basically it is a nonlinear function, and we should not solve it as a linear matrix equation. However, we are still going to do that. And to do that, we will need to use the EFN from the previous iteration into this gamma n. And in fact, by doing that, we will be able to solve for the correct solution. And how this can work? It is because that in this gamma n, we were dividing the Fermi integral with our exponential function. And this will result in a situation that our gamma n does not change drastically during the iteration. So we can still reach a stable solution during our iteration, and the solution does not explode. And similarly, for the whole, we can also apply the same method to write our JP into a function of our stubborn variable. And now we have successfully discretized our Jn or JP, and we can plug it to our continuity equation and construct our finite difference matrix for that. Then since now it is simply a linear matrix, we are just going to solve it as a AX equals to B equation using some linear solver from our Python or other programming languages. And then we will going to do some transfer functions and obtain our EFN or EFP from the stubborn variable. And for boundary condition, there are typically two different kinds of boundary condition. One is the Fermi level boundary or N and P boundary, and another is the current boundary condition. Fermi level boundary condition is a type of Dirichlet boundary. So basically, we will going to define the Fermi level at our boundary point, and then we will going to add this Dirichlet boundary to our right-hand side matrix. And for the current boundary condition, it is the Newman boundary. Since now we are going to give our current value to the boundary, which is giving some value to a derivative. So that is some kind of Newman boundary condition. And to do that, we're going to add some value to the right hand side matrix at 0, 0, and n-1, n-1 point to apply this current boundary condition. And now, how do we solve our Poisson equation and the continuity equation self-consistently? And there are two ways, the Gamow iteration and Newton's method. Gamow iteration is a decoupled method where we're going to solve Poisson equations and the continuity equations separately. So let's say first, we have some initial condition and we solve the Poisson's equation where we will obtain the EC and EV. Then those values will be fed to our continuity equation where we will going to obtain the EFN and EFP, which will again be fed to our Poisson's equation, and we're going to solve these two equations self-consistently until our error of our Poisson equation or for such as EC and EV becomes small enough, and we'll call our solution is converged. And another way to do that is the Newton's method. This Newton's method is same as the one we have talked before. And here we do not solve Poisson and the continuity equations separately. We are going to solve them together. To do that, we'll construct a big matrix where we got this Jacobian matrix of our Poisson and the continuity equations. And those W functions are the function where we are going to solve it. So it is those functions that equals to 0. And similar to our examples from the previous lecture, we're going to solve for delta EC, delta N, and delta P. They are the values, that is the difference between our new solution and the previous solution. And so, compared to the Gamow iteration, Newton's method is less stable, where we are starting from some initial guess that is far from the solution. However, if our initial guess is close to a solution, the speed of getting the solution will be fast for the Newton's method compared to the Gamow iteration. Other than Slalom variable, there is another way to solve drift diffusion equation, which is called the Shafter-Gamow discretization. So here, instead of solving EFN and EFP, we can directly solve for N and P. And to do that, I'm going to use Jn as an example. Let's first just consider the 1D case. And we are going to multiply this equation with exponential bx minus xi to both sides. And by doing that, we can simplify the right-hand side into this simple differential equation, where our b equals to mu n times e over dn. Then now we need to assume that j is nearly constant between I and I plus 1 point, which is true when there is no generation and recombination. And by assuming that, we'll be able to integrate this function on both sides from xi to xi plus delta x point. So since now Jn I plus 0.5 is a constant, we will be able to integrate the left-hand side. And for the right-hand side, it is simpler because we'll only integrate this differential equation. So now, after rearrange this equation, we obtain this form of Jn at I plus 0.5. And we'll be able to plug this into our continuity equation to solve for n or for p if you can follow this method to derive the version of this equation for the whole. So let's compare stubborn variable to the Schafter-Gamow method. Stubborn variable is more concise because we simplify everything into EFN and EFP. And although we derive stubborn variable from Boltzmann approximation, but with some suitable treatment, it can be extended to Fermi-Dirac statistics. Schafter-Gamow method is more generalized since during the derivation we do not assume Boltzmann approximation. But we still need to be careful when we want to apply Fermi-Dirac statistics to it, where we need to consider the Einstein relation under Fermi-Dirac statistics to get correct result. And under heterojunction case, stubborn variable it can be automatically applied since we are going to solve for a continuous Fermi level across this device. So it is more easy to solve for the heterojunction device. But for Schafter-Gamow method, we need to add some additional terms to our drift diffusion equation to consider the spatial difference of the effective mass. Okay, finally, as usual, I'm going to show you some code for this drift diffusion equation. So here I'm implementing the stubborn variable under Boltzmann approximation for the drift diffusion equation. And then after that, it will going to calculate the EFN and the EFP. And I also calculate the Jn and Jp across this device. And then I apply the Gamow iteration to iteratively solve the Poisson and drift diffusion equation. And finally, it will return our EC, EV, EFN, EFP, and the Jn and Jp. And then here is just doing a simple voltage sweep for PN junction from 0 to 1.2 volt. And you can see that here I have applied some initial gas that is based on the physics to help us reach our stable solution more easily. And here is some simulation result. In this simulation, I'm considering the Dirichlet boundary condition for Poisson equation. So you can see that there is some Schottky barrier at these two contacts. And then after apply some voltages, you can see that the barrier of the PN junction is pulled down. So now the current can start to flow. And when we apply even larger voltage, now the series resistance effects start to show up. So voltage drop will cross across this Schottky junction in this PN junction. So when we look at the IV curve, you can see that at large applied voltages, the current starts to saturate due to this series resistance effect.